Welcome to second lecture on nanomaterials. The second lecture is on the basic physics of nanomaterials. The title of that is Quantum Confinement Effect. So it is entirely a quantum mechanics. We need to write so that at the end for this problem we can calculate eigenvalues and eigenfunctions, and then we will try to correlate this to nanomaterials. The problem here is particle in a box. You all have studied this is trivial problem in quantum mechanics. You have studied this problem to calculate eigenvalues and eigenfunctions. For sake of simplicity, here we take one-dimensional case which can be extended to 3 dimension. Now you may be wondering how a basic problem in quantum mechanics, that is particle confined to a box, is relevant to nanomaterials. Particle in a box is a general problem. It refers to many real situations. For example, if we are talking about electron or electrons in a piece of metal, then you can say this is also particle in a box. Electron is a particle and the confinement, that is piece of metal, is a box. Similarly, electron in an atom is nothing but electron is a particle and atom is a box. But you see a huge difference between these two problems, like electron in an atom and electron in a piece of metal. The box for electron in an atom is very confined, very small as compared to the piece of metal. But however, both the problems are quite similar, only what you see is a drastic variation in the confinement, that is size of the box. Let us write basic quantum mechanics of this problem, then try to find eigenvalues and eigenfunctions, and finally we will try to relate this problem to nanomaterials, where a nanoparticle is a box and electron in it is a particle. So the basic formulation of this problem goes as this. You have one dimension here as a horizontal line. There are two boundaries. X equal to 0 is this boundary. X equal to A is another boundary. Therefore, the total length between x equal to 0 and x equal to a is nothing but a. So we can say here a is basically a width of the box. Further, the potential energy within a box of a particle is equal to 0. Therefore, V equal to 0. Outside the box, V becomes infinite. Therefore, on the right side, V equal to infinity. Similarly, on the left side, V equal to infinity. It means the particle cannot come out of the box. It is always confined to the box. The particle can move within the box. The same boundary condition we can write in this way: V of equal to 0 if the particle lies between x equal to 0 and x equal to e. Inside, not equal, but inside x equal to 0 and less than x equal to a. Similarly, V equal to infinity if the particle is above the box, that is x less than 0 or x greater than a. Now we write Schrodinger equation for this problem, which is quite simpler. H psi n equal to En psi n. Here H is a Hamiltonian of the problem, that is operator form of kinetic energy and potential energy. Kinetic energy plus potential energy will give you the Hamiltonian, and this is the wave function of the particle, and what you get is the En into psi n. We call it as eigen equation. En is eigenvalues. Now if you expand this by putting the operator form of Hamiltonian, what you see is minus h cross square divided by 2m, where m is the mass of particle, d2 psi divided by dx square. This minus h cross square divided by 2m d2 square upon dx square is the operator form of kinetic energy, plus V of x, that is potential energy operating on a wave function psi, is equal to what you get is E into psi. Here n has been omitted, but otherwise it is understood that it has n. So the general form of this wave function here, in this case particle in a box, is a combination of sine and cosine functions. Psi equal to a into sine of kx plus b cos of kx. Here k is a wave vector, that is a 2 pi divided by lambda. A and b are the amplitudes associated with the sine and cosine functions. For a free particle, we know that the energy, kinetic energy, can be written as E equal to h cross square divided by 2m into k square. Now you can write this equation in terms of k equal to 2 into 2m E divided by h cross square is to 1 upon 2. Now we can put this the value of k into above equation for the wave function. Result of that is psi of x is equal to a sine of, in the place of k you put its value, 2m E divided by h cross square is to 1 upon 2 multiplied by x. Similarly, we can have the cosine function, that is b into cos of 2m E divided by h cross square is to 1 upon 2 into x. So now we have to take boundary conditions of this problem. As I said in the beginning, that particle exists only in the box, particle doesn't exist outside the box. That is, particle doesn't exist at x equal to 0, that is lower boundary, and also particle doesn't exist at x equal to a, that is upper boundary. Let us take the first condition and try to get solutions. The first condition, that is x equal to 0, if you put this condition x equal to 0, then psi of x will become psi of 0, that is equal to sine function vanishes, therefore you have 0, cos of 0 is equal to 1, therefore plus b. What you have is psi of 0 equal to 0 plus b, that is equal to b. However, at x equal to 0, psi of x or psi of 0 should be equal to 0, hence b equal to 0. So what you get from this first condition is that the amplitude associated with the cosine function goes to 0, hence b equal to 0. So immediately what we get is psi of x, b, amplitude associated with cos function is 0. The result of that is we have only first term, psi of x is equal to a sine of 2me divided by h cross square raised to 1 upon 2 multiplied by x. Now we go to another condition, that is a second boundary condition, that is x equal to a. Again, for this condition x equal to a, psi of a has to be equal to 0. Therefore, if you put in the place of x as a, psi of a is equal to a sine of 2me divided by h cross square raised to 1 upon 2. In the place of x you are putting a, but again particle doesn't exist at the second boundary condition, therefore that also has to be equal to 0. Now what is that we obtained? We have got a multiplied by sine of 2me divided by h cross square raised to 1 upon 2 into a equal to 0. Either it is a equal to 0 or a not equal to 0, so that this function is equal to 0. So we can get either a equal to 0 or this function equal to 0. But we know that a cannot be equal to 0. If a becomes equal to 0, already b has become equal to 0. As a result of that, we do not have any particle in the box. If both the amplitude associated with the sine function and with the cos function becomes equal to 0, it means the particle doesn't exist in a box. Hence, a cannot be equal to 0. The result of that is only this function, that sine function multiplied whatever you have terms here, sine of 2me divided by h cross square is to 1 upon 2 into a should be equal to 0. Well, with that condition, we will come here. Sine of 2me divided by h cross square is to 1 upon 2 into a equal to 0. This can be only equal to 0. It is like sine of theta equal to 0 if and only if theta becomes integral multiple of pi. Hence, 2me divided by h cross square is to 1 upon 2 into a is equal to n into pi, where n is integer. In fact, n can take values from 0, 1, 2, 3 and so on, but we are putting only positive integers without 0. I will come back to this, why 0 is not permitted. Otherwise, in this case, we have n equal to 1, 2, 3, 4, so on, all integer values. Now you can just square it. Therefore, 2me divided by h cross square into a square is equal to pi square into n square. You can write this equation for energy. As a result of that, we can have E equal to h square divided by 8m into a square into n square. Since n is variable here, as I said, n takes values n equal to 1, 2, 3, 4, so on. As a result of that, we can write instead of we can write it as a en. Hence, en equal to h square divided by 8m a square multiplied by n square, where the n can take discrete values starting from 1, 2, 3, 4, so on. This equation en equal to what I have written here is called eigenvalue of this problem. And finally, we can also write the wave function, eigenfunctions belonging to different energy levels of this problem, that is particle in a box. As we know that psi n is equal to a into sine of what we wrote earlier into x, but now you can substitute the value of en into that above equation. Finally, what you get is the eigenfunction, that is a psi n equal to a sine of n pi divided by a into x. So this is what we do in every problem of quantum mechanics. We define problem, we write boundary conditions, then we write Schrodinger equation, try to solve Schrodinger equation so that we finally get eigenvalues and eigenfunctions. So as such, the problem of particle in a box we have solved in a very simple, straightforward way, and what we see is that eigenvalues are discrete because n is going to take discrete values, and for each energy level there is eigenfunction. That is what we have written here. So now we will see the important conclusions what we can get on this problem. I have written a couple of conclusions. The first conclusion, as I said above, though n equal to 0 is permitted as per what we have written earlier condition, but in case of particle in a box it is not permitted, because if I write n equal to 0, I can see immediately the wave function becomes equal to 0, then particle is no more in a box. Hence n not equal to 0 is only the thing we need to write, that is n equal to 1, 2, 3, 4, so on, not n equal to 0. The second conclusion, it's a very important conclusion we can see here, that is we put different values of n in the above equation. If I write an eigenvalue n equal to 1, I can call it as a E1, that is equal to h square divided by 8m a square. If I put n equal to 2, there is a term n square, therefore that will become 4. E2 equal to 4 into h square divided by 8m a square. Now I can try to calculate the difference between the second level and the first level. Therefore I can write E2 minus E1 is nothing but 3 times h square divided by 8m a square. This is actually a very important parameter. We will come to this in a moment. Similarly, I can keep on putting values for n equal to 3, 4, 5, 6, so on. Next we can calculate the difference between third level and second level. Hence we can have E3 minus E2, that is equal to 5 into h square divided by 8m a square. What you see as you calculate the first difference, that is the difference between second level and first level, then the difference between third level and second level. Similarly, you can try to calculate the difference between fourth level and third level, and so on, because you have so many series of energy levels. The main difference what you see is the main parameter that is written within a bracket is constant everywhere it is appearing. Only difference is there is a difference of numerical factor. The first separation is a 3 times of this. The second separation is 5 times of this. Then you go to next separation, again it is more than this. And what we see is we have discrete energy levels, but they are not equally spaced. If you try to draw those energy levels for a one-dimensional case, what you see is a E1, E2, E3. The first separation is a 3 times of that parameter. Second separation is 5 times of this parameter, and it keeps on increases. Hence, we can say energy levels are not equally spaced. Second conclusion here within this is there is a progressive increase in the separation. The separation keeps on increasing as we go to higher and higher energy levels. Let us come to third conclusion. The third conclusion is the term h square divided by 8m into a square. As said in the beginning, a is the dimension of the box, that is width of the one-dimensional box. This in fact is a deciding parameter. This decides the separation between the two consecutive energy levels. As I said earlier, the separation between second and first level is this parameter multiplied by factor 3. So the separation between the two consecutive levels is decided by this parameter, that is h square divided by 8m a square. H is a Planck's constant, that is a fundamental constant. Mass of particle, if you are talking about electron confined to a box, mass of electron is constant. What is important and variable parameter is the width of the box, size of the box. So the conclusion what we draw here, if I write the difference between the two consecutive energy levels as a delta E is inversely related to square of width of the box. That is, delta E is a proportional to 1 upon a raised to square. So what is the conclusion we get here? Larger the size, that is the larger the value of A, smaller the separation between the two consecutive levels. Or oppositely, smaller the size of the box, that is A, larger the separation between the two consecutive levels. What does it mean? It means quantum mechanically permitted values for a particle that is confined to a box, the separation between these two, the energy levels, is decided by the size of the box. It is very, very important conclusion, as I quoted earlier when we started the problem of particle in a box from the quantum mechanics point of view. Though it is a trivial problem, but it is relevant to many real situations. I gave 2 examples. One, particle confined to atom. Atom is a box, particle is electron. Another is a particle confined to piece of metal. Again, particle is electron, box is metal. Metal, piece of metal is very large, extremely larger than the size of atom. In the first case, the confinement is strong. In the second case, the confinement is very, very weak. The result of that is you can change the separation between the consecutive energy levels by changing the size of box. This effect is referred as quantum confinement effect. It shows as you take a material which is in a bulk form, there are electrons which are going to decide certain physical properties of the matter. The size also is very deciding factor. If I try to reduce the size of material, then the optoelectronic properties or the energy levels in the material or the energy levels which are supposed to be accessible to electrons will also getting affected. The result of that is optoelectronic properties of materials will change as you take the material from its bulk to smaller and smaller and ultimately to nano size. Now let us come to the fourth conclusion, that is, for the sake of completeness I have put, even we must put the wave function, that is, already we have written equation for wave function. You can once again draw the energy levels E1, E2, E3, so on, corresponding wave functions psi1, psi2, psi3. The equation what we obtain for wave function, this is how it looks like. Half a wavelength, one wavelength, then it changes like this. And you can keep on writing the wave function for different energy levels. As we know, when we try to calculate any of properties of matter, the density of states, the available density of states to electrons and holes in a matter do play important role. Therefore, the density of states is an important parameter, and many times we try to calculate this and include this for various calculations. It could be related to the vibration of atoms, that is the phonon density, or it could also be related to the calculation of the number of free electrons in a conduction band or holes in valence band. So the simplest definition of density of states is nothing but the number of energy levels in a unit energy interval. If I'm talking about valency band or conduction band, if I take a small interval of energy, how many number of accessible energy levels are available to electrons is nothing but the density of states. In fact, we will see that it is a function of dimensionality. As the dimensionality of material changes, the density of states also gets modified. It means if I take a bulk material, I have three parameters as the bulk parameters, X, Y, Z. But if I try to make material very thin sheet, just like a paper, the thickness becomes much smaller compared to length and breadth. And if the length and breadth are much bigger than the thickness of any material, we can call it as a two-dimensional material. And if we reduce one more dimension of that, either length or breadth, then what you have is only length. We can call such material as one-dimensional material. If we try to reduce that also to a very small size, what we have all three dimensions as very, very small, we can refer such material as a zero-dimensional material. Hence, we can have zero dimension, one dimensional, and three-dimensional and two-dimensional. Therefore, the density of states is significantly affected depending upon the density, depending upon the dimension of the material. So that's why it is written here, it is a function of dimensionality. Now we will try to calculate for one-dimensional case, because already we have solved the problem of particle in a box in a one-dimensional case. Therefore we calculate, and for remaining dimensions simply we will extend it. For example, in a one-dimensional case, just now we have written energy eigenvalues En equal to h square divided by 8m into a square into n square. I can write this as a dE. I take a differentiation of energy with respect to the integer n. H square divided by 8m a square equal to 2n into dn. You can write that dn divided by dE, that is the number of energy levels per unit energy. I said that is the density of states. We write it as a d of E, that is equal to a divided by h root of 2 into m e raised to minus 1 upon 2. This is how the density of states depends on the energy in case of one-dimensional case. Let us draw the conclusion of different dimensions, how the density of states varies for these cases. The first case is a zero dimension, that is, we write it as a 0 dash d. Density of states can be written d of E is equal to sum over EI delta. It is the drag delta function, E minus EI. What you see is you have to put a discrete values of EI. What you get is the discrete energy levels. If you plot a graph of density of states as a function of energy EI, what you get is simply lines. These are nothing but just like energy levels of atom. In fact, atom or a few atoms together we can refer as a zero dimensional material, and the energy levels are very discrete and very similar to what we can have in case of atom. The second case is a one dimensional. Just now we have solved that equation. Density of states d of E equal to sum over EI less than E, E minus EI raised to 1 minus 1 upon 2, that is what we have obtained. And if you plot this equation in the form of graph, d of E as a function of E, what you see is there is peak and keeps on, gradually decreases, again rises, again decreases, and this is how the density of states varies in case of one dimensional case. Then we have the case of 2 dimension and 3 dimension. 2 dimension we write it as a 2D. Density of states can be obtained as a sum over EI less than E is equal to 1. If you convert that to the graph, d of E as function of E, what you get is a staircase like a function. There is the change in the density of states. Finally, 3-dimensional case we write it as a 3D. Density of states can be estimated for bulk material. Density of states for that is proportional to E raised to 1 upon 2 with other factors. What is important is how it depends on energy is important for us. If you plot density of states as function of energy for bulk material, this is how it goes. What is more interesting is we start from 0, 1, 2 and bulk, that is a 3-dimensional. You can see there is a significant modification in density of states. Hence, when we convert bulk material to various types of nanomaterials, 2D, 1D and 0D, density of states is going to significantly get modified. The result of that is the optoelectronic properties of materials will significantly change as we change the dimensionality of material. So let us close this second lecture on nanomaterials.